We'll get started. So I'd like to welcome everyone to this first series of webinars of the LEAP project, the Legacies of Agricultural Pollutants project on integrated assessment of biophysical and socioeconomic controls on water quality in agroecosystems. So this is a project that was funded under the 2016 joint call, or also known as Water JPI. It ran from April 2017 until essentially early this year. So it was originally a 3-year project, but was extended because in part of the COVID-19 pandemic. So my name is Philippe Van Keppen. I'm here at the University of Waterloo, where I'm a professor and a co-PI on this project. Before we start, I'd like to acknowledge that I'm speaking to you from the traditional territory of the neutral Anishinaabe and Haudenosaunee people, and that my home where I'm talking to you from is located on the land promised to the Six Nations of the Grand River. And so I'd like to take this occasion to acknowledge the enduring role of Indigenous people as stewards of our shared land and water resources. So we have this first series of webinars today. So we'll have 3 presentations to discuss or present the outcome of the LEAP project. So we'll have then 2 other series of webinars. The next one will be on Monday, April 19th, and the last one on Friday, April the 23rd. I'd also like then to announce that on the 27th and 28th of April, there will be the final assessment of all the research and development projects that were funded under this joint call. So a few housekeeping issues, and I'll essentially turn it over to Lyndon to give us these housekeeping rules. Lyndon?
Sure. So yeah, welcome everybody. Thanks for coming. Just a couple notes to please keep your microphone muted unless you're speaking, asking questions. You can feel free to leave your camera on or off during the webinar. That's up to you. There may be time for a couple of questions after each presentation, but there will also be lots of time at the end for discussion. So feel free to ask your questions after the presentation or wait until the end if you would like. If you want to ask a question, you can use the raise hand function and then unmute your microphone to speak, or you can write your question into the chat, and Philippe and I will be monitoring that and can read that out. And then also, if you ask a question, please also give your name and affiliation so we know where you're coming from.
All right, thank you. So then for the presenters of today, please try to keep it within 20 minutes presentation so we have some time for discussion afterwards. So the first presentation this morning will be by Nandita Basu, an associate professor at the University of Waterloo, jointly with Kim van Meter, who is now at the University of Illinois in Chicago, where she's an assistant professor and formerly was actually at as a postdoc here at the University of Waterloo. And so their talk will be on modeling nitrogen and phosphorus in Canadian watersheds. And the presentation will be given by Nandita. Nandita, go ahead.
Thank you so much, Philippe. I'm just trying to get my thing in the presenter mode. Just give me 1 second. Good morning, everyone. This work that I will be talking about today was done as a part of the LEAP project. Kim van Meter, like Philippe was talking, who's on the call here today, was the key person kind of with the modeling framework that I'll talk. What I'll talk about today has been submitted in 2 publications, one that Kim has led and one that was led by a master's student in the LEAP project, Joy Liu. We're specifically going to talk about modeling nitrogen and phosphorus legacies in Canadian watersheds. I know there are people here that are not a part of the LEAP project. So I wanted to start off by talking a little bit about the bigger picture before I jumped into our legacy modeling. Of course, the biggest motivation of this work is algal blooms in lakes and in streams and in hypoxia in coastal areas. And the 2 biggest contributors to algal bloom is nitrogen and phosphorus that runs off from our agricultural fields. One of the big issues with algal blooms, as highlighted in this article in CBC News from one particular watershed, Lake Winnipeg Basin in Canada is that despite a lot of effort being made for water quality improvement, we a lot of times don't see a corresponding water quality improvement that we would expect. So this article talks about the fact that despite a 5-year effort, and in this case, I think $18 million were spent, there was less than 1% of phosphorus that was removed from Lake Erie Basin. And this kind of lack of success generates a lot of skepticism. One of the, there's something that's not showing up. Okay, there was an image. Okay, yes. The main hypothesis that drives the work is this idea that intensively managed catchments have legacy stores of nutrients that have built up over decades of fertilizer application, and this contributes to catchment scale time lag. So that's what you see in the image here on the left, where the blue area is the internal memory of the watershed. So you're putting on fertilizers and you've been doing it for multiple decades. Today, if you say, I'm going to reduce fertilizer application, there's still that internal memory that has to deplete before you see an effect on water quality improvement. And the idea of legacy is not a new idea. People have talked about legacies before. The kind of novelty of the LEAP project is to really operationalize the idea of legacies. Can we incorporate legacies in modeling framework, and can we use that to say something about how policy decisions should be taken? So before going a lot into details, I wanted to show you by using some real data as an example how this legacy manifests itself. So this is the Grand River watershed. It's situated on the northern shores of the Lake Erie Basin. It's a primarily agricultural watershed. Everything in green is agricultural, and then you see the pink areas, which are the urban hotspots. You will see me, the entire talk today will focus on the ground because we modeled both nitrogen and phosphorus legacies on the ground. But before going into that, the first thing that we did, and what we do in a lot of our legacy work, is a mass balance. So what you see on the image on the left is a watershed scale mass balance for the Grand River watershed. Now, so this is a 100-year mass balance from 1900 to current. Things above the zero line are the phosphorus inputs. So blue is manure, green is fertilizer, lighter blue is biological nitrogen fixation. And then the orange area is the crop production, which is a negative flux. What I wanted you to draw your attention to is this black line, which is this nitrogen surplus. So which is the difference between the inputs and the outputs. Now, two things to draw from here. One is that we always have a positive nitrogen surplus. We are always putting in more inputs than we are getting out of the system. And one of the kind of rationale behind this legacy idea is that we really need to optimize that nitrogen surplus so that we minimize the surplus values. The other thing that I want you to note in here is that we've been doing a good job in that. So here with the nitrogen surplus, you see that there was a peak in the 1990s, and since then the nitrogen surplus have been dropping. And on the right, the image that you see is that kind of blown up. So this is the nitrogen surplus, that black line. And you see a peak in the 1980s and a drop after that. So that's the nitrogen surplus across the entire watershed. Now, what does the stream nitrate concentration look like? And if you look at that, you will see that nitrate concentration has been increasing. And that's the idea of legacy, that your inputs have been decreasing, but your concentration in the stream has been increasing, and that's attributed to inputs that came in the past. But if you looked a little bit later, you see that nitrogen concentrations have been decreasing. So this is a case of an example of a watershed where there's about a 20-year or so lag time at the watershed scale. Now, the first question that comes to mind is that uniform across the landscape, or does it vary? And in this case, we do see really interesting patterns where you see the Grand River at Brantford, one particular station, where you see the inputs are decreasing, but concentrations are increasing pretty consistently. Another example is the Lower Kanakajee, which is that red dot up there. And in that case, you see a faster response time. The biggest reason why you see the difference between these two stations is that the Kanakaji is a tile drain watershed. So when you have tile drains, you have a faster movement of nutrient through the system and you have a shorter lag time. Using this kind of input-output methodology, in this case, we mapped out the lag time across the Grand River Basin. And in this case, you see the lag times varying from 10 to 30 years. And this is really important when you want to make different kinds of management decisions. Now, this is still talking about the past, right? What are the past lag times? But the biggest question that as a policymaker, somebody is interested in is if we make a change in the landscape, how long will it take for the water quality to improve and how much will be the improvement? So in order to do that, we really need to understand landscape legacies. The first thing that we need to understand is this idea of legacy stores. So given that we know that in a watershed, legacy can accumulate in various landscape elements, then you want to figure out, well, where is this legacy accumulated? So for example, with nitrogen, you can have biogeochemical legacy. This is soil organic nitrogen that's building up in root zone. The biggest source of legacy nitrogen, or one of the big sources of legacy nitrogen, is hydrologic legacy, so groundwater nitrogen. If you're thinking about phosphorus, you can have network legacy, so legacies associated with sediments in reservoirs and in stream channels. So you first need to understand that at the watershed scale, where are these legacies, how much and on what form? And then the next question is, how are these legacies mobilized? And in this case, a changing climate comes into play because a changing climate, more intense precipitation will mobilize these legacies faster in the lakes where it will have an impact. So that is kind of the essence of building the element model, which is the exploration of long-term nutrient trajectories. Before going into the model, the thing that I wanted to kind of talk a little bit about is, if you think about water quality models, there is 10,000 water quality models that are out there. So why build another water quality model? And the main idea behind element model is that if you think about most water quality model, I'll name a common one, which is the soil water assessment tool, or the SWOT model. Technically, you can capture legacy using any model that you want. But to do that, you would have to capture changing land use. So a parcel of land has to go from natural to maybe cropland to maybe urban. And that's not the easiest to do in most modeling frameworks that are available. So that is the rationale of doing element, in which we did a unique way of, say, space-time substitution to be able to capture landscape that has been changing in land use over the past 100 years to quantify how much legacy has accumulated. And if anybody's interested, I can talk further about details of it. Apart from that, it is like most typical watershed models. It's a process-based model. So you add the nitrogen surplus, which I showed you just before. We calculated using agricultural census databases. And this looks as like a small part of a box, but this is in fact one of the toughest things to do in Element, to really go back into historical agricultural census databases and to figure out the nitrogen balance or the phosphorus balance that then becomes input to the Element model. And then you have active and protective soil organic nitrogen, mineralization, convolution through groundwater travel paths to get water quality at the stream outlet. So I'm going to start off talking about nitrogen and then move on to talk about the phosphorus model. So this is element model for in the Grand River watershed. And in this case, we developed the element model for 15 basins in the Grand. What I'm not talking about here because of lack of time is other work that we've done with the element before. So we worked with element for the Mississippi Basin and the Chesapeake Bay watershed, where we used element to predict water quality. Due to lack of time, I'm not going into that. So in this case, we developed element for 15 basins in the Grand. So that's what you see on the right. That's the network of basins that we developed. And the purple is the main stem of the Grand. And this is kind of showing that river network. And these are the various tributaries, and they are connected. So this is really interesting because the Grand is one of the most monitored watersheds around here, which allows us to have this huge amount of data to be able to run the element model as at the nested watershed scale. And this work was done by Joy Liu, who was a master's student in the group. She's now has started her first position out. And so to begin with, we again did a mass balance. So what you see on the left is the nitrogen surplus for various subbasins in the Grand. And overall, the two things to take away from that is that the patterns are really similar because agriculture has progressed in a similar way across this landscape. But the actual magnitudes of nitrogen surplus are, of course, very different because we have some in here that are more natural forested watersheds, while others are more ag-dominated watersheds. And on the right, what you see is, again, components of the nitrogen surplus. So this is more manure driven. So this is just shown for the entire basin. Now, this is then used as inputs to develop models for, again, all the subbasins in the Grand. And overall, the model does a good job. So the red data points are the data, and the black line that connects to them is the model predictions, and the gray is the uncertainty bound. So overall, the model captures the trajectories fairly well. So the next thing that we wanted to do, which is one of the most interesting things with this work, is to figure out how to use the model to estimate the legacy accumulated. So what you see on the left-hand image over here is cumulative nitrogen fluxes and stores across the basin. So the left one is just for the entire Grand River watershed. The black line is the cumulative nitrogen surplus. So this is the unaccounted for nitrogen. What we see, of course, the gray area, which is the stream nitrogen load, is a significant part of it. The purple, which is the wastewater, is a small portion. There's a huge amount of landscape denitrification. Groundwater nitrogen accumulation is a small amount. Of course, the biggest amount that stays in is soil organic nitrogen. And this is important from a management perspective because this is soil organic nitrogen that has built up in this landscape, which means if you have various nutrient management practices where you apply less fertilizers, you can tap into this reservoir of soil organic nitrogen. And on the right-hand side is the variability. So what we did is, if you look at the last point line over here, those proportions, but we did it for the various sub-watersheds within the Grand. And as you see, there's of course variability within the sub-watersheds, but overall, your landscape scale denitrification and soil organic nitrogen accumulation is some of the largest components. Just as a simple kind of point. So the top one over here is, as an example, the Kanakaji. It's a very tile-drained watershed. So of course you can see the stream nitrogen load is a big portion of the surplus in there, whereas landscape denitrification is less than some other watersheds in the system that are more forested. Okay, so then the next question we have asked is, well, now we have 15 watersheds. How can we use this to scale up over all the watersheds within the Grand River Basin? So what we did to do that is we looked at correlation. We said, what does the fraction of nitrogen surplus that accumulates in groundwater depends on, and the fraction of nitrogen surplus that accumulates as soil organic nitrogen depend on. And I'm not going to talk about all the correlations. We played around with many numbers, but at the end of the day, what we found is that the mean travel time, the calibrated mean travel time, was the strongest control. So the R-square values are high and the p-values are reasonable for us to think that this was a reasonable relationship. And then the other thing that we found is that the tile-drained area, of course, is the biggest control of that travel time. With when you have higher tile-drained area, your travel time decreases, and that makes sense because it's short circuits through the landscape. So this image on the right kind of captures what tile drains do, is that they change the balance between mineralization and denitrification. So they alter the soil organic nitrogen accumulation, but they also route the water out of the landscape and alter the groundwater accumulation portion. Using these correlations developed, we now can say what is the soil organic nitrogen accumulation across the entire basin at the sub-watershed scale, and that's what you see. And again, the patterns are similar to what you have seen before, with the groundwater accumulation a smaller fraction and the soil organic nitrogen a larger fraction. The next step, what we did with it is we wanted to say, well, what does that mean moving forward in time? And that's what you see over here. We did different scenarios. The 3 scenarios are business as usual, 50% ag surplus reduction, and 100% ag surplus reduction. And how the end loading changed. And the main thing that I want you to take away from here is, as you would expect, but we see this also in model results, that as legacy N decreases, the amount of nitrogen loading decrease you get. As legacy N increases, you see lesser nitrogen loading decrease in 2040. So your lag times actually increase in the landscape. Okay. Now I'm going to switch elements on you from nitrogen to phosphorus. The nitrogen model, so the nitrogen model is what we have worked on for the longest time. So that's why we did it at this fine scale. The phosphorus model is relatively new and was actually developed during the LEAP project. And so this one, we've done only 1 watershed, but the results are really interesting. So this is the phosphorus mass balance, again, the same watershed, the Grand River watershed. And again, here you see the manure is one of the biggest components of the mass budget. The other thing important with phosphorus is that phosphorus surplus has been decreasing significantly. The phosphorus mass balance model, the phosphorus model is similar to nitrogen. We have organic phosphorus, active and protected pool, and mineral phosphorus. When we think about phosphorus, we also have to think about erosion and retention in reservoirs and riparian areas. And there's also groundwater travel times through the landscape. The other big deal about the phosphorus model is the domestic component. So here's just an example of the complexities in terms of doing it. When you think about phosphorus, there's detergent phosphorus in dish and laundry detergents. There's also food. Some of that goes through food waste and goes into the landfills. You also have households that are on septic systems or wastewater treatment plants, and those proportions change over time. Wastewater treatment plants have biosolids that go to cropland. Septics have biosolids that go to cropland, and then you have proportions going into surface water. So all that has to be taken into account for that human component. And that this is a snippet of what you see over here. The purple is the food waste, the human waste that has been increasing over time. But the yellow line is the domestic phosphorus loading to rivers. So even though human waste has been increasing, what you see in the yellow line is an indication of our tremendous ability to treat the human waste today. So this is the improvement in wastewater treatment plants. So despite this increase in population, water quality due to this hasn't really changed much. And if you put that in context of the entire watershed's water budget, the domestic phosphorus is really a small portion of that budget. So if you want to treat this problem, at least in this landscape, you should need to focus on the blue and the yellow parts, which is the domestic, which is the manure and the fertilizer. Won't go into a lot of details, but this is the model for the outlet of the Grand, and of course, and the phosphorus modeling is more complicated than the nitrogen modeling because you have nonlinear absorption, desorption processes, and retention. So this modeling took much more work to be able to pull together, and many painful coding from chem. The biggest thing about models like this is models like this tell us where the phosphorus is hiding. So in this case, you see a lot of the phosphorus has accumulated in the soil. And just to give you an idea of numbers, in the Grand, we find that only 4% of the net phosphorus input has been exported to downstream waters. So most of this has been accumulated in the landscape as legacy phosphorus. Now, the other part of what we are interested in doing here is to try to say, can we validate these estimates? So in this case, you see that the reservoirs and riparian areas is a significant part of the estimate of legacy phosphorus. And we did this work in collaboration with a professor in biology who does these sediment cores, Professor Roland Hall. And what we did over here is took a sediment core, did lead 210 dating of the sediment core to understand the sedimentation rate in the reservoir. And in this case, the sedimentation rate was 50 tons per year, which translated to 38 kilograms per hectare of upstream area. And when we converted those numbers to phosphorus, we found that that based on the data, we were saying it was accumulating 38 kilograms per hectare of upstream area. Our model predicted a really close number without any calibration to that number. So this basically says that in the mean, we're able to capture these retention erosion dynamics fairly well with a modeling framework like this. Of course, then the next point is how do we think about the future predictions? And this is a lot of different scenarios. So I'll walk you quickly through it while not going over my time, which I am over. So we did a range of different scenarios. Business as usual, where the current phosphorus use efficiency is 63%. Phosphorus use efficiency means how much phosphorus is taken up by crops versus how much you put on the landscape. Scenario 2, where we increase that a lot, but we don't see any decrease in loading. And this is because, again, of legacy phosphorus. The biggest change we see in the system is scenario 4, where we altered the manure handling loss. So manure, after it's produced, there is some losses associated with handling. It's a small fraction of the manure, but because there's so much manure generated in the landscape, and because this is a direct input to your stream, when you change that, that has a big impact. And then this one was 80% wastewater treatment plant improvement and 20% reduction in erosion. So any one of them was not able to associate the 40% reduction in phosphorus loading. But if you add it up, scenarios D, E, and F, so you have no manure handling loss, 80% wastewater treatment plant, 20% decrease in erosion, you start getting that, the 40% reduction. So bottom line, phosphorus, there's a lot of legacy accumulated, so improvement would take longer, and we'd have to think outside the box than just reduction in fertilizer application. So just one last slide, not too much. So now with work done by another student, now not on LEAP project, on a different project, we are doing this across the Lake Erie Basin. So thinking about inputs and outputs. So what you see over here is various stations within the Lake Erie Basin where we are looking at concentration trajectories and load trajectories, and ideally would develop element model. So with that, I would like to thank you for your time. And if you have questions.
Sure. Thank you so much, Nandita, for this very clear presentation. Yeah, the floor is open for questions. So if you have a question, you can raise your hand or even raise your voice would already be sufficient. I don't see any hands up. Does anyone have comments or questions? If not, I'd like to ask you, and this is not, no, I see Brian has his hand up. Brian, can you ask your question? You have to unmute. You have to unmute.
Yeah. I hope I'm unmuted now. I was just wondering, thank you for a very clear presentation. I was just wondering in terms of the application of phosphorus, you showed there was a surplus of the application in terms of the manure and the fertilizer. Is that, let's say, deliberately, or is that, do farmers actually think they need this surplus, or is it mainly to get rid of manure? We've had the same issue in Denmark for years, that you're just trying to get rid of manure, but now with the phosphorus planning coming into place as well, there will be more focus on this. So have you had the same, let's say, history on this, or could you say a little bit more on this?
Absolutely, Brian. Yeah, so you hit the point right on the head. One of the biggest reason is manure, right? As you see, it's a big component of the budget, and it's produced more concentrated, so you have these manure hotspots. So that's one of the biggest reasons. But also, I mean, fertilizer is cheap, so there has been a move towards educating farmers to apply less because there is surplus in the landscape, but there is variability in space. So there's uncertainties about how much is needed and how much is too much, and questions about that. And I think in terms of general, I would say application and general some of these BMPs, I think we're much behind where Denmark is in terms of getting buy-in, in terms of reduction in application. But it's kind of packaged as this nutrient management strategy. So farmers send in data about their levels in the soil, and based on that, they are suggested different kinds of nutrient management.
One last question from anyone? So maybe just a question, comment. As you showed, I mean, there's of course the Grand River watershed is particularly high phosphorus accumulation place or watershed. It's not necessarily the same for other watersheds in Ontario. So there is, of course, as you said, thinking outside the box. I mean, the transfer of manure phosphorus from one watershed to another watershed. Or other options like there's been suggestions to essentially ship manure out to the open ocean and basically fertilize the ocean and reduce the CO2 in that fashion. Do you see that those ideas will ultimately have to be taken seriously and considered as options?
So I don't know about the manure shipping, but we actually have, so one of the biggest things that I think is necessary with manure problem, and Kim and I have been working on this with a master's student at the US scale, and we've also gotten a project funded now to do it in Ontario, this idea of manure shipping and manure to biogas. Because there is too much, it is concentrated, and we need to figure out better structures and better policy frameworks to handle it, whether it is through trucking it to somebody else's fields, which right now is done, but only within a short radius because it's economically not feasible, or whether it is trucking to a biogas plant, but that definitely needs to happen. Kim, do you have? Kim, feel free to jump in on thoughts.
Yeah, I would just reiterate what you're saying. I think that some of this shipping manure around is being considered. I know that's something that's being done in the Chesapeake Bay watersheds, where there's a lot of really intensive poultry production near the urban areas, and a lot of manure buildup and not enough land to spread. So some of that is being trucked out of the Chesapeake watersheds, but you're exactly right. The problem comes with the economic feasibility of that.
Okay, let's avoid the phosphorus tax discussion right now. Okay, so thank you again very much, Kim and Andita. So we'll now go to the next presentation by João Marques from the University of Coimbra in Portugal, who will be talking about nitrogen and the Mondego watershed. Go ahead.
Thank you. I'd like to confirm if, can you see my screen?
Yes, I can see it. Yeah.
Okay,
yeah.
thanks.
Great, thank you.
My name is João, and my presentation is about the nitrogen loads and legacies in the Mondego watershed. The authors of this work are me, Joy, from University of Waterloo, Maria from Portugal, from University of Coimbra, and Kim and Andita, also from Canada. The main purpose of this work is to quantify the nitrogen time lags in the Mondego River watershed in Portugal. To quantify these lags, we need to determine how the nitrogen inputs and outputs have changed in last centuries, and we need to compute the accumulation and depletion of nitrogen in soil and in groundwater. The Mondego watershed has been considerably changed by human actions, by the construction of large dams, and by the construction of infrastructures to improve the agricultural conditions. This is a short story of the watershed. Since the 14th century, there were frequent floods with severe consequences in terms of loss of human lives, infrastructures, and crops. Sorry. This then there was, in the 18th century, a first attempt to prevent the floods by the regularization of the river margin as this straight red line in this figure, but this solution did not work. Then in the 60s, there was another attempt, the Mondego watershed hydraulic master plan, with the regularization of the river flow by the construction of dams, by changing also the river course, and by constructing systems for flooding control in extreme situations. In addition, there was also an agricultural plan in the 80s to improve the farming conditions in this area. So, before the plan, there were frequent floods, not only in the crop areas, but also in urban areas that caused severe consequences. And the agriculture practice was very traditional, with little mechanized, and farmers using animals and workforce for agricultural activities. With the implementation of the plan, large dams were built, as the Gueira, Raiva, and Fronhas dam. They were built in the upper part. This upper part is in the light green. This is the light green area that is very hilly, with narrow valleys. And after Coimbra, more specifically after this Sud dam point, the river flows slowly and with very gentle slopes. This orange part is the low Mondego. All these infrastructures were inaugurated in the beginning of the 80s. Here we show a picture of the Sud dam that is considered the division point between the upper and the lower part of the basin. And this is also the location where the water used for crop irrigation of low Mondego is collected. These are pictures after the implementation of the plan with the Mondego River watercourse, and also a picture with the water channel used for crop irrigation. These are more pictures in the end section of the irrigation channel, where the unused water is returned to the river main course. So once the hydrological regime of the river was controlled, the project for the agricultural development in low Mondego was prepared for the improvement of the agricultural conditions. The areas at green and red represent agricultural blocks with a total area of 2,000 hectares. Those at green were intervened, and those at red are still to be concluded. The interventions were related with the construction of irrigation, drainage, and road networks, and by the implementation of land consolidation programs. Here we have an example of a block where there were more than 1,000 parcels, and after the land consolidation, the number of parcels is expected to decrease to 220. So here we have some pictures with infrastructures already built as roads in the agricultural areas and also irrigation points. So describe the watershed. We now move to the used approach. Here we use the element model described previously by Nandita. To do this is necessary to compute the imbalance for different land use types. Element consider three different kinds of land uses: the cropland, where the nitrogen surplus is determined considering 4 terms, input terms and 1 output term. Input terms are the biological fixation, the inorganic fertilization, manure, and the atmospheric deposition. And the output term refers to the unincorporated in crops that are harvested. A second term is pasture that considers the same previous 4 terms as inputs, but in the pasture areas, and also output term that is related with the grazing by animals. We also have a third term that represents other areas of the basin that is given by summing the contribution of biological nitrogen fixation of no agricultural lands with the atmospheric deposition. The sum of these three terms plus the contribution of the wastewater produced by residents represents the total surplus produced in the basin. With this, we can estimate using the nitrogen loading trajectories in the outlet. So to quantify the end surplus, we need to gather data, for example, as the number of residents. Here we can see that growth of the number of residents was different in the low and upper parts of the basin, where there was a high increase in the lower part that doubled since 1864 to 2016. Then in the upper part with an increase of 60%. This can be associated with the lower part is more urban than the upper part, it's a more rural area. Regarding the organic and inorganic fertilization, livestock is used to assess the organic fertilization. These are the number of animals from different species in thousands. Cattle increased until the 70s and 80s and then decreased. For pigs, we have the same kind of trajectories that can be observed. In the case of goats, sheep, and equine, there was always a decline in the number of animals, and the equine has a drastic reduction that can be mainly associated with the substitution of this kind of animals of the workforce working in the agriculture by the machinery. Poultry and rabbits also increase until the 50s and then decrease with different trajectories. In terms of inorganic fertilization, it was considered that it started on the 50s. So here we have the cultivated areas with cultures with capacity of biological fixation that also have decreased. The crops considered were beans, chickpeas, broad beans, and peas. And in fact, these are not common crops in Mondego. Just here one example of broad beans sown in Mondego and the nodules of nitrogen on its roots. This figure, this is the figure with the most important crops in the basin. In the low part, most important are maize and rice that are cultivated in the agricultural blocks, and potatoes and forage are also important cultures. In the upper Mondego, the most important are maize, olive trees, and vineyards. These occupy 50% of the total agricultural area. As stated, in the low Mondego, the most important crops are maize and rice. The rice culture is only practiced in the agriculture blocks, as you can see here, by the green areas that are totally inside the limits of the agricultural blocks. In the case of maize, this culture is also practiced in other areas, but is prevailing inside the block limits. So moving, these are pictures of the most important cultures in the upper Mondego. This is a highly area, and vineyards and olive trees are cultures that can be used in this kind of landscapes. In fact, there are important demarcated wine regions hands down in this part of the basin. So collecting the data, we can compute the nitrogen inputs in the basin. The N inputs have decreased over periods, mainly related with decrease of the agricultural activity and also by the implementation of best management practices to limit the chemical fertilization use. This can also be related with the delay of improving the agricultural conditions, as 35% of the area in the agricultural blocks are still to be improved. And this has contributed to some abandonment of the agriculture. The higher reduction of the N inputs in the upper part may be related with higher losses of agricultural areas when compared with the lower part. So now we reach to the element results. And in this figure, we have the contribution of all the terms for computing the N surplus that is represented here by the black line. This line can be divided in three main trajectories. In the first 1.5 century, there was a low variation of the N surplus, but then it increases until the beginning of the 90s. This was mainly related with the increase of the inorganic fertilization use. And then after 1993, the N surplus trajectory starts to decrease due to the decrease of almost all components of the N surplus. So then the element model was calibrated by fitting a set of parameters to reproduce the nitrate and loadings at Mondego water outlet. And this figure shows the observed at black, and the simulated load at red, and also the discharge of the Mondego at blue. For the periods with available water quality data. These red and black lines, you can see that follow the discharge line at blue. And also from this figure, we can state that the element model was able to provide a good estimate for the nitrate loading at the Mondego watershed. This graph includes the fluxes in the case of Mondego. The highest nitrogen losses we can see that are related to the denitrification processes. And in terms of soil, we can see that until the 70s, there was a soil and depletion. This is because the soil was a source of mineralized N, but then with the increase of the fertilizers use, the soil became N sink in the recent decades. Relatively to the groundwater, there was always an accumulation, a positive N flux entering in this kind of water bodies. As we see, the nitrogen legacy are function of the mean groundwater travel time. In this case, the element result is that this is equal to 19 years. As already stated, the N surplus increases until the 1993 and then start to decrease. And this is shown by this blue area in this figure. And we can see that this trend is not observed by the nitrates in the outlet that are represented here by these orange points. In this case, this increased until the first decade of the new millennium, but then start to decrease. This difference might attest that there are legacy effects that are taking place in the Mondego watershed. So now we reach at the conclusions. We studied how the N inputs and outputs have changed in Mondego in these last 2 centuries, that the N surplus have remained practically unaltered during 150 years, but then start to increase until the 90s, mainly associated with the use of chemical fertilizers. Then this N surplus decrease due to decrease of the agricultural activities, and this can also be associated to the with the social structure that changed. In fact, the population previously engaged in agriculture has moved to other more profitable areas, activities in urban areas. We can also say that the higher nitrogen losses are related to the nitrification processes that is common in watersheds that have high forest areas, warm temperatures, and large dams, as in the case of Mondego, and that there was negligible accumulation of N in soils, and thus legacy effects can be more associated to the groundwater nitrogen accumulation. Finally, in this work, we can conclude that these legacies have an order of magnitude of 2 decades in this Mondego watershed. Thank you very much for your attention.
Thank you very much, Darrell, for, again, a very nice presentation, very clear presentation. Are there questions, comments? If not, I maybe add one more technical question. I mean, we know that, for instance, at least in rice cultures in very many countries, the rice culture itself stimulates denitrification very often because you have kind of these water-saturated soils. Here you seem to imply that it's mostly because of the forested areas, the natural areas. Can you comment on that?
Yes, yeah, it can also be a reason for us to have so high denitrification percentage, and it's true that rice, the flooded areas in rice also increase this kind of processes. Okay. It's also a conclusion that we can take. Thanks.
Okay. All right. Anyone else? Because otherwise, I had more of a kind of a speculative question. I mean, you clearly, I mean, what's interesting about the Mondego Basin is, of course, that it's an area where we could say agriculture is in decline, right? As you pointed out. Do you think that in the future there might be? Is there a future for agriculture in the Mondego Basin? You think it's because you also showed, for instance, the wine cultures. Well, I know that worldwide wine culture is increasing.
Yeah, yes, maybe because things are always changing, and if the socials, maybe also the social structure changes, and the most attention is given to agriculture and some kind of crops, as the vineyards, for example, maybe this kind of trajectory of decreasing the agriculture areas could change. And in future, I think it's possible to change this kind of trajectory. I don't know if Maria wants to say something about this.
I believe this is really an uncertain situation because the wine region is in the upper part of Mondego. That is a very hilly part, and the areas that can be cultivated are very small. I believe we cannot increase too much this part to have the additional vineyards. I'm not sure, but as far as I know, by observing the landscape, I would get this conclusion. Right. And in the low part, the problem is completely different. It's just rice and maize. And really, there was here a problem, a social economic problem, because this population of Low Mondego waited a lot by the intervention that could improve the agriculture area in the Low Mondego part. However, it takes too long to the plans to be improved. I have to say that this low area, we have the historic documents speaking about the erosion in the upper part that gave rise to floods documents even from the 13th century. So this is a real problem in the Low Mondego. So these people was waiting for an intervention to be possible to have, I would say, largest areas for a more intensive agriculture to turn from a familiar agriculture to a more industrial agriculture. The point is that it took too much time, and meanwhile, and this is the main reason for this change in social structure, there was the Carnation Revolution. So new opportunities were opened to this population of Mondego in urban areas. We have analyzed the pendular moves from the population of the rural areas every day to come to Coimbra to work. So the conditions were not enough improved, it takes too much, and new social economic conditions were generated by this Carnation Revolution. All the farmers left because they were old, and there was no young generation to replace them. So these are the main reason. That's to say, probably if the initial project for the management of agriculture aspects was really implemented in due time, probably the situation will be different, but we never know, because really the Carnation Revolution introduced a really, I would say, good change in general.
Okay, Maria, we need to stop here.
Thank you. Thank you.
Thank you for the extra details. Brian, you have your hand up?
Well, it was just a question. When you compare with the Canada and perhaps also Sweden, I don't know yet, but do you feel like you're in a very sort of lucky spot? Some of the nitrogen levels and even the phosphorus levels is very low. So is that just you showed part of the reasons, but I mean forestry and everything. But do you also do you also feel that you're in a lucky position, an easy position?
May I say just a word? We made some calculations to understand if all the Mondego area that would be improved through the plan was really improved, if this was sustainable from the point of the environmental parameters. And it could be done. It could have been done with no problems for the environmental parameters. So the reasons are different reasons.
All right. Thank you. So we're actually right on time. So I'd like now to ask Jörg Joseph from Stockholm University to talk us about the Swedish studies.
Thank you. Let's see.
Okay. All right, you can see your slides.
Okay, yes, I hope you can see the screen now. So my name is Jörg Joseph. I'm professor in hydrology at Stockholm University. And other members of the Swedish group is Benoit Deserer, who's a postdoc working in the project, and Georgia Destoni, also a professor at the same department, physical geography, at Stockholm University. And the work I'm going to present is collaboration work. So we've had very important interactions with essentially all the groups in this project, and the modeling work has been done in close collaboration with the University of Waterloo. So I'm going to start a little bit wide. I mean, you can see actually, I'll go back to this picture, you can see the site that we're going to be focused on. It starts in the Stockholm area, the capital area, and extends towards more rural areas. So here is actually a suburban area where you have this mixture of rural area, and Stockholm is growing, and you have all these kinds of processes going on. And you also see actually some measures being taken here, environmental measures. These are like constructed wetlands that the municipality has organized, and that's one possible measure that is being discussed now to expand, the wetland areas, to get more desertification and stop nutrients from reaching the Baltic Sea. So I took this picture actually from a post right next to the wetland. And as you can see, they also speak about here like biological diversity, and they speak about lots of things. So in this project, we have a focus on nutrients. But then when we go and we look at measures, you know, sometimes we have like conflicts with other environmental goals. And I think that's a topic I will return shortly to in the end of my talk. So the main objectives now that I will focus on is like what we developed with the legacy nutrient toolbox, including diagnostic tests for legacy pollutants. We will look also at long-term nutrient budgets, including the element modeling, which is a great opportunity now to have same tool for different sites in different countries, and we can really compare the results. And I will also talk a little bit about vulnerability, so we know where the net inputs are, but how about the vulnerability to, for instance, the Baltic Sea and so on in different spots. And I will, in the end, again, relate to measures. So for instance, the wetlands and what can be done to improve water quality in the Swedish context. And the main example I will use is the Norrström watershed. So it's situated here, as you can see, the capital, Stockholm, is here. And it has an area of a little bit more than 20,000 square kilometers. The outlet is in Stockholm, but actually, so we have a close-up here. There are also some artificial channels here for ships going into the lake. So it's a little bit special. It has several outlets, but most of the flow goes here. So it drains to the Baltic Sea. It contributes to the severe eutrophication problem of the Baltic Sea, which is a main focus of Sweden's environmental strategies to reduce these nutrients flows. And we can note that we have two major lakes within this watershed, one here and one very close to the outlet. And we will see this in the results as well. And if we look a little bit at the land use, we can see that it's rather mixed. I mean, it's one of the main actually agricultural areas, so the yellow parts here. But we have in the upper to the north, we have rather large forested areas, and we have some major towns. Actually, 3 out of 4 major towns in Sweden are basically located here, or let's say 3 out of 5. And Stockholm is here. So the agriculture, if we look at the time, it peaked in the 20s, the agricultural land. And then we have had, due to competition with the urbanization and so on, slightly less areas since then. We can look at, here again, it's just a schematic picture of the processes going on with the agricultural inputs. This is a schematic view of the legacy pollutants building up, for instance, in the volume of the groundwater. And then we also have our urban contributions. And a huge progress was made in the 70s or late 60s, early 70s, when we started to build wastewater treatment plants. And then in the latest 20 years, we got like harder environmental targets. And the challenge now is to, go down even further in nitrogen loads, phosphorus loads to meet those targets, which is largely set up by the European Water Framework Directive, which we actually, we should comply to that directive. So this is the challenge now. We can see just one example close to Stockholm, how a phosphorus measurement series can look. from the 1970s here to 2016 or 2013. And it's apparent that, you know, when we started to have sewage water treatment, it really went down a lot. The concentrations in the stream. So this is a stream outlet before the major lake of Mälaren. And then somewhere here, we started to, you know, think about the framework directive. It became implemented here. Already we started to implement all kinds of measures to further bring down the concentrations. But you can see on this curve that essentially not much happened. I mean, the improvement is a little bit hard to see. And it is actually way above the good status mark of 21 micrograms per liter, which is the green line here. So we're somewhere away from the target. What we did now also was to look at all the data sources to compile nutrient input data for nitrogen and phosphorus. It's a bit complicated with the structure. There is certain data in the counties, as you can see to the left here. We have some data in the municipalities. There are more municipalities. And there is even some data in parishes or hundreds. And there are lots of them. And they have some detailed data on what we need to make these budgets. You can get an overview also. It's well monitored, this region, compared to many places in Sweden. We have hydrological measurement stations by the Swedish Meteorological and Hydrological Institute in pink. We have water quality measurements in green here at several places. So it means that we can actually do balances also for sub-watersheds here. To get a grasp on the variability within the basin, which is interesting. So again, the inputs here, land use, crop production, livestock, and atmospheric deposition, and all kinds also hydrological input that we compiled with Nandita also and Kim at Waterloo. We looked at this, and I will present two results here, like for the whole Norrström basin, so the outlet here, and for an example where we have a lot of agriculture, so an agricultural intense area, to contrast the average to see if we have regional differences. And here we can see in the intense area, we have about 50% cropland, but still some forest. Whereas as in the basin as a whole, as you saw earlier, we really have quite a substantial amount of forest. And these mass balances are from the 1850s. So as you can see now in the intense area, we have similar notation as you saw in earlier presentation with the colors. So we have the livestock contribution in blue. We have the mineral fertilizer. These are the main inputs nowadays. And we have biological fixation. And also the most important line is the black net surplus of nitrogen. And what we can see here is, of course, an increase in the livestock and manure. The mineral fertilizer is stabilizing a little bit, but not really going down a lot. We have currently a surplus that is higher than in the 1850s in these agriculturally intense areas. For the whole basin, it's actually a little bit different. So here, I think this is a difference from the Canadian case, that here we also have a slightly different, not just in magnitude, but in trends. So if you look at the whole basin and the net surplus, we actually have a decrease in the basin as a whole. So here, the present surplus is lower than the 1850s, in contrast to the agricultural intense area. So slightly different trends. And mainly you can see in the whole basin this livestock manure, the blue bars, they really decrease since the 1950s. So then the calibrated estimates of catchment characteristics. We look at travel times, the nitrification rates, and for groundwater and for human waste. And again, in the intense areas, we can see really different characteristics. We have rather quick transport, so retention times 2 to 5 years. And this is the most frequent results from the model output, so around 2.5 years. We don't have that much denitrification, between 2 and 70% annually, with most common value 6%. And the sewage treatment is not perfect. I mean, there's a lot of farms, there's a lot of private solutions. So we have an efficient about 45%. In the whole basin as a whole, we have much longer retention times. And we think this might be a lake effect because we had rather little lakes in this intense area, whereas in the whole basin, we do have these large principal lakes. There might be other factors too. We have a higher denitrification rate, much higher. And the sewage treatment is good on average. I mean, the big urban areas, they have functioning solutions and they don't contribute to the problems in the catchments. So interestingly, we see a lot of contrasts within our catchment areas. I will move on also to then the phosphorus situation. There we have slightly shorter time series, so around 15-20 years. And this is the work that was led by Tamara van Staden from University of Waterloo, who did an exchange with us. We're now in the process of making a paper of this. And we can see this is just an illustration now to see the spatial variability in the net inputs of phosphorus. And actually we see a gradient here also within our basin. So the urban areas to the east, we actually have a decrease or like depletion of phosphorus in net, whereas we still have increase in the western areas of the basin. And that can very easily also be seen if we look at the frequency of years with positive phosphorus input. And we see almost all the years in the west, we have like a net increase, whereas actually it doesn't happen very often in the east. So this is the overall picture we have, doesn't show on this picture, but we have a slightly decreasing overall trend in net input over these years. What we compared with here is also to introduce the dimension of vulnerability. So this is a vulnerability map that was created where we consider, how might this net input be transported further on. So then you need to have surface water nearby. You have higher risk of, reaching the Baltic Sea. Depends on the precipitation patterns, which may differ within the basin. And actually, tile drainage is very important. We found an important factor, and it was mentioned earlier. So to get a good model here, we need to get a grasp on the tile drainage system, which is tricky. It's very local, and we needed to do some assumptions. What you can see, however, is that, probably considering all these factors, there are systematic trends within the basin. We tend to have higher vulnerabilities, more red areas in some parts of the basin, to the west here, also to the east. And we tend not to have it in the forested areas in the northwest though. So this means probably if you use different data, you can look at the high input of fertilizers, you can combine it with the vulnerability, and you can kind of identify areas where maybe you should make the measures or have priority of making measures, which would be in the southwest in this case. We also looked at some ways of doing diagnostic testing. So all these slides I showed so far builds on a lot of data and a lot of data compilation. And maybe we can use to get a grasp on if we have a big storage in groundwater or not, if we have slow or quick flow paths, we could look at individual hydrological events or look at high discharge occasions. And we can look at how, for instance, salinity or chloride behaves. So if you get higher water flows, do you also get higher mass flows of chloride? It tells you something about where your source is. So if you have under certain, I won't go into detail here because time is short, but under certain assumptions, you can get the result that, if you have a linear relation between tracer mass flux or chloride in this case and discharge, then you're likely to have sources, legacy sources and storage. So look at the dynamics and maybe you can get a quick test to see if you are at risk of having high stores of chloride and other substances. And in our case, we get consistent results with the more detailed element modeling that we did. So we can see if we add the data, we compare with, you can see different model assumptions here. In the end, in the lower part of this graph, you can see it's model just synthetic data where we assume that there is no legacy and we don't get this increase. So the only way we can fit the model to the data is to assume that we get about 80% of the chloride mass from legacy sources, so through the slow parts of the system. So that was nice to be able to make that comparison. Briefly, the last minutes of my talk, I want also to introduce, how is this knowledge from scientists transferred to practice in municipalities and by various decision makers. And we have made interviews, and we actually made this just before the start of this project. And then we interpreted the results of the interviews with respect to the legacy problem. And, the practitioners were asked questions about the Water Framework Directive. What did they learn? What are the practices? What are the collaborations they have? How is knowledge generated in your water collaboration in the municipality? And importantly, how do you deal with uncertainties? The scientists are good at this. We think, at least, we don't know. But if you have a practical problem, you need to take a decision. So how do they deal with that? I mean, in more sharp context. And we interviewed more than 20 interviews, I think, with different kinds of actors, civil servants in the municipality, health inspectors, steering committees of environmental committees, and then non-governmental organizations. There's a fishing association and so on. And the main output from this was that there is actually a certain knowledge fragmentation because we have a complex structure with the European perspective, but it's a very local decisions in many times. In Sweden, we have a strong municipalities. They have a lot of right to do things, but it means that knowledge is out in many regions. That's the drawback of this. And often they use consultants, and it means that the complexity sometimes can get lost because the knowledge is with the consultants and they get exchanged and so on. And we couldn't see evidence, much evidence of specific attention to legacy sources, which we think is really important for the problem. So that's kind of an issue. So we need some kind of critical evaluation of how we deal with water quality issues in municipalities in Sweden, as well as in water districts. And just to tie back to the where we started with this picture of the wetlands, there is a huge interest on using wetlands now as solution to various problems, including eutrophication. One reason you can see here is the Norrström Basin, and here in purple are the wetland areas. And you can see that locally there is actually a lot of wetlands. So the idea is, could you use them? Could you manipulate them somehow, flow through them, to use them to reduce nutrient loads? And you have different kinds of wetlands, and you know, this could actually be something that governments would be ready to invest in. And the background, of course, is that we don't know how these large systems of wetlands functions. We have good scientific knowledge of individual wetlands, but how would these solutions work at larger scale? And another thing that comes into play here is that, of course, now we have different economic processes relevant for recreation of wetlands. So the geometries and the location of wetlands might be, you know, governed by the economic and social processes and not by the landscape forming processes that form natural wetlands. And this is actually an issue because it determines how much flow that could run through the wetland. And just some example of you know, different motives for making wetlands. One motive is actually that there is a lot of money available. You can, as a private person, apply online on a web formula to get money to dig your wetland on your farm. And many farmers do this. So they might think about hydroclimatic change if they are really into the issues, right? And they want to do something good about the environment. Sometimes when you ask people, it could be like, you know, one could see here, they get a nice view from the kitchen window. They might be interested in the local biodiversity. You could go ice skating here in the winter. And some people might be concerned about the pollution. So there's a range of reasons for creating wetlands. And the question is this a good thing or a bad thing for nutrient retention? So I'll skip this one and just go to forward-looking last slide on like the monitoring efforts. We think that we need more monitoring effort in wetlands to be able to, you know, understand better how they work as a solution. And this is a solution that is now being implemented. So we were able to attract research money for this, where we put water level meters, measurements in hundreds of wetlands. We get the data online and we can reconstruct the travel times and so on to support our modeling. So that's an interesting aspect for scaling, I think. So in the end, what we saw is actually that preliminary size matters of wetlands. If we have larger wetlands, the effect is larger, not only as a simple scaling, but also because we get recirculation of water, you know, one water particle and the nutrients pass through multiple wetlands, and you get a better efficiency through having larger areas. And then we have open questions on how to design the wetlands for different purposes. And I think I'll end there and to kind of keep my time. Thank you a lot.
Thank you, Jerker. Thank you very much. Yeah, the floor is open for questions or comments. I had a question about the wetland stuff, because I could imagine that if you have existing farmland and you start, say, transforming it into a wetland, at least initially, it could be a strong source of things like phosphorus, for instance.
Yes.
And so there's also going to be some kind of a a legacy effect of in that sense, so that the benefits could be delayed for a significant amount of time.
That's right. Yeah. Essentially, you increase the travel times.
Yeah,
So,
that's one way to look at it. Yeah, you look at it as a hydrologist, of course. That's interesting. Okay. Yeah. Other comments or questions?
Should I just jump in? Great presentation, Jarkko. So I had a quick question about the wetland part too. So, so you are looking at water levels of hundreds of wetlands, and are you looking at, so when you say that small wetlands were more efficient in nutrient retention, were you actually measuring like input-output fluxes from these wetlands in terms of?
We have, yes. No, we have not. We have some wetlands where we measure in great detail the input, the output, the bathymetry and everything.
Right.
And we need to calibrate the model against those.
Right.
Which we only partly did.
Okay.
And then we can say something about the larger scale. As for now, what we can say is that the parameters are favorable in larger wetland areas. So if you look at the travel times, the transit times, conditions should be more, in theory, favorable for nutrient, to get rid of nitrogen from the water.
Cool.
But this is ongoing work.
Yeah.
And it will be interesting to see if our theories are correct. Yeah.
Okay.
I have a question, if I may.
Go ahead.
My name is Birgitte Hansen, and I'm from Geological Survey of Denmark and Greenland. And thank you for these very interesting presentations. It was very great. I have a question to you, Jørgen. You talked about effective denitrification as a percentage per year. And I was just wondering, how have you defined it? These rates?
Yeah, it's this effective attenuation constant. So in the equations, it comes as a decay.
Yeah, between the road zone and the outlet, or what?
Oh, this is effective. So this is large scale. So it's actually, we calibrate the model to the observations in the outlet.
Okay.
So this means that somewhere in the basin, these processes happen. And this is the effective result.
Okay, so it's between the surplus, or what is your input? Is it surplus or nitrogen surplus? Or is it kilo nitrogen per hectare, something like that?
Wait, I can actually get back to the slide. I think that might be informative. Let's see if I can share this again. Share screen. Okay, do you see my presentation now?
Yes.
And then we have a look at this slide. So here you can see the input of the different, these are quantifications being made, and then the calibration is for the output concentrations.
Okay.
So this is, my understanding of it. The actual modeling and the model development was done by Benoit and Nandita and Kim. Okay. I think I answered the questions. Do you want to add something?
Maybe I could specify this particular number for loss of nitrogen that we called the nitrification here is along mainly the groundwater pathway in the element model. Okay. So not really the soil dynamics, but the longer term transport term, the convolution term that has been presented by Nandita and John. Okay.
Thanks a lot.
It might step in to clarify the question. So the nitrogen surplus is the input to the model. Then there is a carbon nitrogen cycling in the soil that surplus feeds into. And then there is denitrification in the soil. And then there is a flux that goes to the groundwater. And then there is groundwater. So what you see is an effective denitrification rate in the groundwater and an effective denitrification rate in the soil across the entire watershed.
Okay, thanks a lot for these explanations. Very interesting.
Thank you for the question. Okay, we're just 1 minute over time, so I'll close the this webinar session right here. As you saw in the chat, we will be posting these webinars on the website, the LEAP website, so you'll be having access to it. And then what I would like to ask then maybe at some point is also if the presenters can send me also their slides so they can prepare also the presentation to the whole GPI secretariat. So and I hope to welcome everybody then at our next webinar series, which will be on Monday, April 19th, starting at the same time. So I hope everybody has a great day and hope to see everybody again on April the 19th. Thank you very much.
Thanks, everybody.
Bye.
Thank you. Bye.